let's go ahead. We had the housing, and now we would like to start with wire bonding. We had point number 8, and here wire bonding, and we should think about how we could do it. In our sketch, we have said it is a ball wedge bond. And we have said it is gold. And what would be an appropriate diameter? So typically, I would say 25 micrometer is something that is well suited. The question is, how does it work, and what are important parameters? So when you wire bond with gold, you can say 25 micrometer is sufficient, because our circuit is only a sensor which has no significant power consumption, and it is an IC which typically also has only a few watt of power consumption. So we could say normally 25 micrometer bonding wire is sufficient. Okay. Now for the bonding process, the geometry we would like to have is like, if this is the metallization, we would like to have some bond which looks like this if it's a, let's say, a very small loop. And the question, what are the individual steps? The first step is, of course, when we have the tool, we have the wire protruding, we flame it off, so we make a ball. Later on, the whole thing is pressed onto the substrate, onto that metallization, and then the loop is formed, and the final deformation which we get is something like this. This wire is pressed under here, and in that way, here, of course, the tool must have that shape. In that way, the loop is formed to that side. So, and not so beautiful, but I think one can see what is important here. And in that way, we have first the ball and then the wedge. So we have the individual steps. So flame off. First bond, loop, second bond, and finally we tear off the whole thing. and in that way we can make a loop and go from bond to bond. So the next question is, what are relevant process parameters? So which kind of bonding can we have in ball wedge with respect to energies? Do you have an idea? And these energies also determine process parameters. Please speak louder. Yes, very good. So when we come back, so for instance here we can say we heat. So typically we have the temperature. So temperature is typically below 300 degrees centigrade. Often it's maybe between 100 and 200, depending on the material. What is the second parameter? Yes, what you can set is what you can set at the machine is the force. Yes, sometimes it's called bonding pressure. Pressure is always a force per area. So it's somewhere in the, let's say, centinewton range. So that means you have several grams of bonding force. What else is important? If you have only these parameters, it's thermocompression. But what else do we have in the bonding, typically? What will the tool do? Yes, so we have a movement. Yes, don't be deceived, that is only below 1 micrometer. Normally it is not measured. It is very hard to measure such amplitudes. So typically we set the power of the bonder. Of the ultrasound. So that's typically in the few watt range, but in many bonders you cannot give the watt number, but you just give a setting, yeah, between 1 and 100, so you give a percentage. What is the last parameter we have for that bonding? That's the time. That's the time of ultrasound action. And so we have principally 4 parameters. There are more parameters, for instance, like the tool radius or the frequency of the bonder, but these are typically values that are constant. So now let's go back to our list. So then we can fill up the package with silicone. silicone filling. For instance, we use needle dispenser. And afterwards we heat. There are many possibilities to heat, let's say somewhere between 100 degrees centigrade and just as a guess 2 hours, up to 150 degrees centigrade and maybe 15 minutes or so. Because you already have a relatively big part, yeah? So because it's a package, so you cannot have too short hardening times because you always need some time to heat up the whole thing. Eleven is we place the lid and we weld, and that could be ultrasonic welding, laser beam welding. It also could be gluing or just pressing a hot element onto that material. In these cases, we have a local fusion and also when we have a hot element. Then we have 12 glue onto heatsink. So in that case, again, we could say, okay, it's very similar, like like 8. So in that way, we pick and place. And for example, 120, 1 hour, or such a typical temperature. So we are finished with the production, and now we can start with going for the design tasks we have here. And as we could say in our task, we have that gyroscope. So it is, I just look up the number 62, which we have here. A 2-chip solution for the gyroscope, and now we have the thermal conditions. With the design, you must solve the technical problem of thermal management of the microcontroller with equivalent thermal circuit. And that is based on that also the solder joint reliability of the controller. But first we have the thermal aspect, and to that purpose it is important to know about the individual layers which we have here. So what we have is a flip chip, and that flip chip is on a printed wiring board. That printed wiring board is glued onto the base plate, which is, for instance, made of copper. That is glued onto the heatsink, which we have here. So we have the base plate. We have again an adhesive. And under that we have the sink. And on top of that whole thing, we have the silicone, and we have the lid. Okay. What is missing? We have the silicon here. And also we could say we have an underfiller here, but you are allowed to neglect that underfiller. So we have the following layered system, which we can show now. It is where will the heat go now? The heat is dissipated here in the flip chip. The active layer is here. The heat will go through the flip chips. It will distribute here, at least partly. It will then go through the adhesive. It will distribute in the base plate, if that base plate is larger. And then it will go in here, and finally, by convection, it is dissipated to the air. Okay, and in that way, the first thing we should think about is how could we get that solved? Now we have forgotten something, because the heat will go also upward. It will distribute a little in the silicone, and finally it will go through the lid. And as a last step, again, we have the dissipation of heat to the air of the environment. And a good concept to solve that problem is the concept of thermal resistance. Okay. The maximum junction temperature must not be higher than 150 degrees centigrade, and the power is 2 watt. Also, that air here has a temperature of 50 degrees centigrade. That's also important. And here we must say the maximum temperature in that layer it must be lower or equal to 150 degrees centigrade. So that's our design task we have here. And the concept is that of thermal resistance. What is thermal resistance? Do you have an idea? How is resistance defined? Resistance is typically the voltage divided by the current. The thermal resistance uses an equivalent, and that is more or less the potential difference. So that is, maybe here I write better delta U on the resistor, and here I write delta T on a resistor divided by the power that is dissipated. So our allowed delta T is how much? T junction minus T ambient, and that is 150 degrees centigrade minus 50 degrees centigrade. So the delta T, which we can allow as a maximum, is 100 Kelvin. Okay. In that way, we can also define what the maximum allowed thermal resistance is. Yeah. So it must be smaller than, what is it? 100 Kelvin divided by 2 watt, and that is 50 Kelvin per watt. So that RTH is a property of our package. And now our task is to find out what this RTH is. Do you have an idea how we could find that? So we have the materials, we have the thermal conductivity. Typically the sign for this is lambda, but we also need the geometry, yes? Typically we can say the thermal resistance of an element which has the area A and the thickness of D and the thermal conductivity of lambda. For such an element, the RTH is D divided by lambda A. That can be just derived from some law of heat conduction, and in that way we could have the idea just to put together our whole package just of many blocks, and in that way to compute the individual thermal resistors which we have here. So geometry means area A and thickness D, and that are typical values in assembly and packaging. And now we, as you pointed out, we can make a series of resistors. In fact, in our case, we must make also a parallel switching of our resistors. So we could say, if we have here some voltage source, so that's the ambient here, 50 degree, then we have several resistors. So here we have the junction, and from the junction we first go into the resistor of the solder. We do not go into the silicon because we go upward through the silicon. That's different when we have a wire bonded assembly, because in that case the heat also goes through the silicon. But here it goes, it's down, and here it's the up branch here. So that's a silicon. Now maybe it's simpler first to go up. From the silicon we go to the silicone. And from the silicone we go to this PA6 lid. And from there we go into the convection against air, and then we come against the environment, so air. On the other hand, solder, we go into the printed wiring board. We go into the adhesive. We go into the copper. We go into the adhesive. We can do the heatsink itself. And then we again go to the air. So, in fact, what we must compute is the resistances for both branches, and here you can do, for instance, then you can say 1 divided by RTH is up plus 1 divided by okay. So in that way we can say the RTH of all RE up and the RTH down so in that way we can do that, and in your exam you will have a table, so you can say 1, 2, how many layers do we have? 1, 2, 3, 4, 5, 6, 7. 10, 11, quite a lot. Normally you can make a more simple design so you do not have so much to compute. Go ahead. So you have the material. Yeah, please. Of course. Yeah. So yes, the starting point was the sketch. Yeah, I said that's a junction junction here. Yeah, and that has a maximum temperature, and the heat always is flowing from hot to cold. Yeah, and the cold in both cases is the ambient air of 50 degrees centigrade. So what we must model is from the layer. So here you could say that is also your heat source. Yeah. From here down you must make resistors. Yeah. So you make resistors here and so on. So in fact it's a crude simplification, I must say, but still it works fine. And each of these resistors is modeled by such a block. Maybe I forgot one thing which is important, of course. In that block, the heat goes that way. Yeah. So it has a certain resistance. When you would say there are more blocks in a series, then of course you just add up the resistances. On the other hand, the heat also goes up here. Yeah, here you have resistors here, and so you have two paths of your heat, one going down, one going up, and in that way you can model it. What you can do is, and that is important when you make assumptions for the area, you cannot normally take the whole area because the heat is concentrated more in the middle. And also when you look at the final heat sink in real life, it always will be hotter in locations directly under the chip. Yeah. So, but on the other hand, the heat is spreaded, and here in our exam and the exercise, we will just make assumptions. Yeah. So for the area and for the thickness. And of course we must assign thermal conductivity. And in that way we can say, okay, that is the up and that is the down. And in that way we can model it. We must assign the individual areas. For instance, when we look at the area of the chip, so here we would start with the silicon. We already have a certain area given for that task. For instance, do we have some size of the controller? No, it's not given, so you must make a reasonable estimate. So what would be a good estimate for a silicon chip for a small microcontroller? Some are given and some you must estimate as is just state of the art. So for instance, say 5 millimeters square or such a thing, yeah? I advise you strongly that in all data you give here, you just give in units meter, yeah? So the millimeter is just to show it to you what is reasonable, but in reality, please take 25 times 10 to the power of -6 square meter. And also for the thickness, what is a typical thickness of such a chip? Let's say 200 micrometer, so it would be something like 0.2 millimeter. But on the other hand, it's better to use just the meters, because why is it so? For instance, when we take for the silicon, a heat conductivity, for instance, we would say 120 watt per meter Kelvin, and so you will be not in danger of mixing up millimeters and meters, yeah? And so in that way, you can just easily compute the RTH, which is given in Kelvin per watt. So it's 25 divided by 0.25. What is it? That is something like 120 or so. So again, RTH is and in that way you can compute it. For the solder, for instance, so let's say it's a SAC. What is a typical bump? Here you could say the following. What is a typical bump size? Yes, you could, for instance, say also it's something like 0.2 millimeter, just as an example. And what would be the area? You could compute it based on the geometry, which is a ball, but you could also say maybe just 25% of the area is SAC. So you could say 25% or 20% of 25 micrometer square. So that would be, for instance, something like 5 millimeter square. Yeah. So the thickness you have the thermal conductivity of the solder, and in that way you can compute it. What I will not do in this exercise now is compute all of the individual values. Also, I have no calculator with me. What is still important is the convection. And so that's how the heat goes against the air. And in convection, the thermal resistance is just 1 divided by area times H, where H is the heat transfer coefficient. And these values we will just have to see. For instance, you would say in your example, just as a guess, 10, a value of 10. And that heat transfer coefficient is given in what? So H is given in per Kelvin and square meter. So that means if you have 1 Kelvin of temperature difference over that interface that has 1 square meter of area, then 1 watt can flow over that interface. So in that way, you can compute your table. Based on that table, you will get the RTH, which is a total RTH, and the Tmax that you get is RTH times the power plus the temperature of the ambient. So example, what have we seen? We have allowed a maximum value of 50. So example, RTH, let's say, is 40 Kelvin per watt. So Tmax is 80, 40 times 2 Kelvin plus 50 degrees centigrade. So it is 130 degrees centigrade. So in that way, I would like to see the maximum temperature, and in that way we have solved that whole thing, and just doing the calculations is something that you can do for yourself. Okay, do you have question with respect to this part of the exercise? Go ahead, please. No, for most of the materials you should have a guess. Yes, what is important? One thing is how thick is such a layer. There you can make an estimation. Let's say a typical printed wiring board is 1 millimeter or 0.5 millimeter or such a thing. And also there are some typical values. Also you will find a table of material data in the lecture notes on the last page. Yeah. Maybe you do not need all of the data, but the most important ones you should have in mind for that exercise, to solve that. Yes. Sorry, can you repeat it, please? But you could have the lecture notes. You just have to take it from our lab, yes. I have, but I distributed that information. I have sufficient of lecture notes you can get there. I can also give you that table anyway. That's not a problem. That's just a guess for such materials data. Okay, is that clear for you? Okay, so we are now finishing. Also, I think more on the theoretical part of thermal management, and so I can make it a little shorter because we have already seen the basics of this. The rest also you could read in the lecture notes. Yes, so we still have 3 weeks, and that is sufficient to get all through the exercises and also through the lecture notes. Okay, for today, if there are no more questions, then I say thank you for your attention and see you on the coming Monday. Okay, goodbye.